Hello again, everyone. This question is from Conceptual Dynamics textbook, and we are going to answer this question. In the following figure, mass C is attached to a rope that is wrapped around the outer edge of drum B. As mass C falls, the rope around the drum unrolls without slipping, causing the drum to rotate. This in turn causes pulley A to rotate due to the belt connecting the drum's inner radius and the pulley. Consider that mass C is released from rest and reaches a velocity of 1 meter per second after it has fallen 30 centimeters. If the mass accelerates at a constant rate, find for the instant shown the magnitude of the acceleration of point P on the outer surface of the drum. So before we answer this question, let's sort out the information. Here I have collected all information that we need to answer part A. So first of all, the velocity of point P will be the same velocity that mass C has. That's why Vc is equal to Vp. At the beginning, the mass C was released from rest, and when it reaches 1 meter per second in velocity, it falls 0.3 meters. That's why at the point that mass C reaches velocity 1 meter per second, point P will have the same velocity, and at that incident we want to find acceleration. AR and AT are the two components of acceleration at point P, because mass C is accelerating. That's why every single point on this outer surface of the drum will have the same acceleration and velocity that mass C has. So if we draw these two components here at point P for AT, this is vector AT, tangential acceleration, because the drum is rotating that way, mass moves downward, and we have another component for acceleration, which is radial acceleration. So the superposition of these two, AT and AR, gives us vector acceleration at of point P, and this vector is basically vector A. So the vector of acceleration of point P can be written as A radial unit vector in radial direction plus AT E theta unit vector in tangential direction, and the magnitude of acceleration will be a square root of AR squared plus AT squared. And We just need to find AR and AT and plug in this equation to find the magnitude of acceleration of point P. So let's start with AR. AR is from previous lectures. We have VP squared over RB. VP, velocity of point P. And when it reaches 0.3 meters, that velocity is 1 meter per second. So let's use that velocity and find AR. 1 meter per second to the power of 2 over RB is 1.2 meters. 1.2 meters, and then we get for AR 0.83 meters per second squared. AT is the same as acceleration of mass c. But what is acceleration of mass c? To find it, we can use this equation from, again, cinematics. VCF squared minus VCI squared equals 2AC y. This is y, which is 0.3 meters. So this gives us AT is equal to AC as VCF squared minus VCI squared over 2y. If we substitute VCI, which is 0, and VCF, which is 1 meter per second, and also y, that is 0.3, we get 1 meter squared per second squared minus 0 over 0.6 meters. And the final result will be 1.67 meter per second squared for AT. And this is for AR. We just need to plug in this equation. So the vector of acceleration of point P will be 0.83 meters per second squared ER hat plus 1.67 meters per second squared E theta hat. So we just need to find the magnitude of this vector by using this equation. So this gives us A at point P, the square root of 0.83 meters per second squared to the power of 2 plus 1.67 meters per second squared to the power of 2, and ultimately we get acceleration of point P as, after calculating this square root, we get 1.86 meters per second squared. This is for part A. For part B, we are looking for angular velocity and angular acceleration of drum B. So the drum B, which rotates in this direction, has angular velocity omega b and angular acceleration of alpha b. Omega b and alpha b can be found by this formula: v at point P equals r b omega b, and a t tangential acceleration as r b alpha b. We can find omega b as v at point P over rb, but v at point P is the final velocity that we had in part A over rb. One meter per second over rb is 1.2 meters, and then we get 0.83 radians per second. For alpha b, we get AT over RB from this equation, and by substituting AT that we found in part A as 1.67 meters per second squared over 1.2 meters, we get 1.39 radians per second squared. So this is omega b, and this one is alpha b, or angular acceleration of drum b. Let's focus on part C. We are looking for angular velocity and angular acceleration of pulley A, this pulley. So before we answer this question, we should know that all points on this belt have the same velocity, and also they have the same acceleration. For example, if you consider one point here on drum B, on the interior radius in contact with the belt, like point S, and 1 point on the belt in contact to pulley A, like S prime, then velocity of belt at point S is the same as velocity of belt at point S prime. And also acceleration of belt at point S is the same as acceleration of belt at point S prime. So these two equations help us to answer part C, and to find the values we should just substitute instead of Vs as R B omega B equals RA omega A. From this equation we get for omega A the ratio of RB over RA times omega B that we found it before. So that's why omega A will be, for RB we have 1 meter, for RA we have 0.5 meters, and for omega B we found it as 0.83 radians per second. That's why after calculating this we get 1.66 radians per second. This is omega for pulley A. And for the acceleration, we know that A is equal to R alpha. So R B alpha B, because this is acceleration of this point, and this is equal to RA alpha A for acceleration of point S prime on pulley A. So as a result, alpha A will be RB over RA times alpha B. Again, if we substitute the quantities, get 1 meter over 0.5 meters times 1.39 radians per second, and ultimately we get 2.78 radians per second squared for angular acceleration of pulley A. Thanks for watching.